introduction to TCP flow control. I just assume not all of you are very familiar with TCP, so just introduce some basic features and others. Why TCP is used in so many places? Because it's different from other protocols in some places. First of all, it's very, the most important is it's very reliable because it has many mechanisms to make TCP can reliable send data and receive data. I will introduce this later. Another feature is connection oriented. It means before you send data, you have construct a connection, and for different applications, you must use different TCP connections. For example, if you use telnet and all you use FTP, they all use different connections. So it's connection oriented. It has byte stream. It has a byte stream control because TCP have a sequence number marked for each byte, so it can send very reliable each byte in. You can send every packet without loss. Let's introduce some basic features. First is accumulative acknowledgement. I think all of you know the TCP have a TCP header has a field of acknowledgement, and it will send acknowledgement for each packet it received. So you can make sure how many packets it has received. If it lost, you can retransmit it. What is the cumulative acknowledgement? It means when you send acknowledgement, you don't send exactly the sequence number of each packet. You just send the packet you received in order. It means if you receive out of order packet, you will not send the sequence number of that packet. You just send what you received in order. So it is called a cumulative acknowledgement. Another very important feature is the sliding window. Because each TCP has a very important flow control mechanism, and is the send window and receive window. Send window is it means how many packets you can send without acknowledgement. It means you can send a full window packet. You need not wait for an egg. But after that, you have to wait for acknowledgement, and then you can resend more. So the sliding window is the flow control post on the sender side. Suppose we have a window size of 7 packets, and after so you can send without egg. So you send 3 packets. Then you send the window become 4 packets. And after that, you receive an acknowledgement. Oh, yeah, no. This part send an acknowledgement, but it haven't received. It just keeps sending. So to send 2 packets at this side. So the sliding window become 2 packets. It means you can continue send 2 packets without an acknowledgement. And when you received and acknowledge. So you can increase the window size by 1. It means one packet have left the network, so you can send 1 packet more to the network. When you send all these packets and receive the acknowledge for the 7th packet, as I have said, it's an accumulative ACK. It only sends ACK for the highest secret number you have received. So, because you receive an acknowledgement for the 7th packet, it means all the 7 packets have left our network. So the flag window becomes 7. So
you don't show all ACKs, of course. You just show 2 ACKs, not more.
I suppose the other ACK have lost.
Okay.
Maybe it lost, maybe it have not received.
So notice what happens. You can lose the ACKs, and it's going to be fine. If you lost the first ACKs, then you had a problem. What should talk about?
Another feature is the self-clocking. It means the sender send the packet based on what you received about the acknowledgement. When you can send a window of packet at the receiver side, but you can send more only after you receive an acknowledgement from the receiver. So the whole flow is self-clocking. It means your send speed is controlled by the speed you receive acknowledgement. The acknowledgement you receive more faster, you can send more faster. This is called self-clocking.
What is the meaning of a piece of a bit?
I think it's the length of the packet, or the time take to one packet to transfer from it. This is bottleneck link. Each packet is controlled by. It means the space between the acknowledger is the same as the space between each packet, because this is bottleneck link. You cannot send faster than this bottleneck link. Let's introduce some flow control.
Escape.
Escape, yeah, I think it's good.
It only has the Ethernet explorer.
No. Do you know?
And Explorer would work too, I mean, if you don't care.
Yeah. Then Internet Explorer, Microsoft. This one?
blow it up to the whole thin size.
Here is a good website about TCP. And this is what we say the connection-oriented TCP connection. This is the introduction about TCP header. Each TCP header have a sequence number. It marked for each byte of the TCP packet, and have an acknowledgement number. This number is the acknowledgement tell the sender how many packets it have received. And this is control bit. It's just when the ACK bit is set, it means this packet is an acknowledgement. There is a checksum bit to make sure every packet is sent without error in this data field. Flow chart is the TCP state transition datagram, but it's will not impact the flow control, so we will omit this. This is what we say sliding window. From this picture.
Well, I think you have this Microsoft something, PowerPoint ready.
I want to show a picture about the slow start and the congestion control. Picture about slow start. Slow start. This plot is about the send window. You just see what it means, sliding window. Slow start means you start with a very small.
You explained the axis. What are the axes?
It means you start with a window size of very small, like one packet or two packets. It means when you start to transfer, you have no idea how the network is congested. So you can try to send packet and increase the window size slowly, because the window size means how many packets you can push to the network without acknowledging. It means the total packet you can send in the network. So the slow start means you increase the window size for every acknowledgement you received. When you receive one acknowledgement, you increase the window size to 2. When you receive all the 2 acknowledgements, you increase the window size to 4. So you see the curve is increased exponentially. And at this point, it has a name. It means the slow start window threshold. When you reach this threshold, you cannot increase window so fast. So you just increase the window size minimally. And until sometime a congestion happens, means you have realized that some packet is lost. So you just decrease the window to the lower point, and you keep increase it slowly. That is what we say slow start in a congestion. not sure.
So actually, when you reach congestion and you decrease window size, by how
Yeah.
much do you do that by?
Half of the current window size.
That's for faster transmission.
Okay, so that's once you reach that green point.
No, the green point at first, it's something that's a parameter in TCP, and it is set up by the operating system or whatever. You know it, yes, up front. So if nothing happens, everything is fine. This first picture, it shows it very nicely. There is this parameter called SS thresh, and you go up to it fast, which is slow step is exponential. It's kind of funny thing. And then you slow down, okay? And you keep increasing, trying how much luck you have. And if there is no too much traffic, and then you hit traffic, then you lose something. And then Hongbo will tell you there are two cases. Either you can retransmit, you can do faster retransmission after losses, or you really have nothing from your other side until time out, and then the procedure is slightly different. But like she says, you always have to reduce your window, because network seems to be congested. Remember, TCP is all designed about congestion avoidance. You lost something, it meant it was congested. So, and it's nice, it's fair. So you need to back off.
Okay.
The take-home message is that TCP tries to probe it in the network, how fast it can go. And
To come back to what you said, TCP does set the level, the threshold level.
implementation of TCP, yeah, it's just a number.
Right.
Just a number, how many bytes you can send until you have to go into, what is the window size really it means, until you can have to go to the slow start, to congestion avoidance, which is a limit.
So is this like a number that everything on the internet has, or
No.
is it on a per? It depends on like the network. The guy who sets up the network card.
Actually, not the network. It depends on
Or the-
how you set the host. Yeah.
Oh, it's not real time?
No, this SS thresh has two things. It has a value at the beginning when you open a connection, or when you boot a machine, okay? And it depends on the implementation. It is not mandated by RHCs. It's recommended to be like, what, 64 MSSs? I forgot. It's a recommendation what should be the value of SS thresh, and it's totally left undefined.
Oh, yeah, the latest one will be 2851.
Yeah, did it say something what should be the value about SS thresh or not?
It just the flash size, half of flash size.
No, the initial value.
Initial value is no limit.
No, yeah, it's not limited. It's really implementation
Yeah.
dependent. The point is, you see that as soon as you hit the congestion, Hongbo explained it will go down to half the value. Right?
So you don't want to set it too high because you'll overshoot it.
You will create a long queue of packets somewhere, and it will not help you too much. So kind of.
Because the window size is eventually restricted by the receiver buffer size. It means you cannot send more packets than the receiver can receive. This buffer size is carried by the acknowledgement. It means the acknowledger has one field to say how many bytes the receiver can receive. So it doesn't matter the threshold is how large or not.
Could you explain in detail this type of plots? What is the meaning of access? Because the sequence plots are one of the basic tools in analyzing TCP. So if you could spend a moment explaining how to understand this plot.
The blue dot means the data packet you send. The red
Begin with
one,
axis. What's on the axis? Because people may not see it's very tiny letters. What is the x-axis and y-axis?
this is the timeline, and this is the sequence number. And the blue dot means the sequence number of the first byte of the packet. You can treat this as one data packet. And the red one is acknowledged, it received. This plot can show very clearly how slow start works. Slow start means you increase your window size when you receive each ACK. From the beginning, you send one packet and you receive one ACK. And then you can send two packets, then you receive two acknowledgements. So you can send 4 packets, and then you receive, after you receive the 4 acknowledgements, so you increase the window to 8 packets. And until you meet a packet loss here. And then you receive a duplicate ACK. This is caused by the accumulative acknowledgement mechanism, because when you receive some packet and out of order, I mean you lost this packet, so you cannot receive this packet, so the acknowledgement and the ACK number always be this packet, so you receive accumulative ACK. After you receive 3 acknowledgement, you enter to a state means faster retransmission, because there is a high possibility you lost this packet, although you don't know if you really lost or not. You just guess it's lost. So you faster retransmit this packet here. And then you receive acknowledgement for this packet because it's accumulative. You have received all these packets, so you just send an acknowledgement for this packet. And after that, you decrease the window. You decrease the window size to 1. But because you receive this acknowledgement, so the window size is 2 at this point. And after that, you enter a slow start again. You increase the window size exponentially. So the window size is 2, 4, and here it's 7. In fact, if it keep in fact, this is 7 packets just because the threshold is 7. So you can't increase very fast at this moment. And after that, you increase the 1 packet only after you receive all these acknowledgements. This is congestion avoidance.
If I may add something. This is really tricky and it takes some doing to understand it, but this is extremely helpful to understand what happens. As she showed in the preceding graphics, that SS thresh drops down. The moment when you change from fast slow start to congestion avoidance, that it changes after a loss. So when she has fast retransmission, it was a loss. Notice that window was 16 at this moment. But it was halved. It went down back to a half of its value. So now she cannot grow that fast anymore because you switch to congestion avoidance at 8 at this moment. You see? That's why she has slow. Yeah. That's how it's not shown on this graph. This web pages that she shows you has these graphs too, at the stretch stuff. But it's kind of cool how this thing constantly adapts itself.
In the graph, they don't show the retransmission. So it's not.
Oh, it is. It's just hidden under. It happens on the same red little line of axis. There are encapsulated PostScript files with this graph. It's very open, so you can blow it up in Ghost View and see. In this resolution, you won't see it because it had the same sequence number as the axis. You see, so it's like overlaid with the points. You just can't see it, but it is there.
Yeah. From this picture, you can see the congestion. This is congestion window plot. The congestion window increase exponentially until it hit this point. This is threshold. At first, you set it with a very high value, and only after a congestion happens, you should decrease it. This is receiver window size. Because you decrease it to the half of the smaller of these two, and because the receive window is smaller, so you decrease to the half of the receiver window size. So the threshold becomes the congestion window is decreased to 1 packet, and it's doing slow start. After it hits the threshold, it begins to increase linearly, not slow. This is congestion avoidance.
What's the pink line?
The pink line is the receiver window size. It means the buffer size of the receiver.
You see, when we establish a connection, I don't think it's time and necessary to tell how connection is established in great detail, but it's a ping pong. I send you a packet called SYN, which says, I want to open a connection to you, and that's my starting sequence number. We have to agree on that. And you answer me and say, this is my starting sequence number, and by the way, that's my advertised window. So that I don't send you more data that you can access. That's the kind of idea.
Yeah, here is the idea. What do we say to set the threshold to the half of flight size? Flight size means how many packets is in transit, means it is in the network. And the flight size is the minimum of these two values. One is congestion window, one is the receiver window. Because you cannot send more packets bigger than these two. So the flight size is the smaller value of these two values. Congestion window is the flow control posted by the sender, and the receiver window is the flow control posted by the receiver. So the window size controlled by these two.
I have a question. Why the blue line can beyond the receiver buffer line, and that blue line, why can beyond the pink line?
Because the blue line can increase, no restriction. Because this is only controlled by the sender. It knows nothing about the receiver.
No.
Before the handshake?
No. It happens in time. You do not send the number of packets, and you know it. Well, I know that you know it. There is a thing called, which is sort of the effective window. On one, from the top, it is bounded by the smaller of congestion window and advertised window. Yeah. But it also has a bottom. And this bottom is determined how many packets you have already sent. So I don't think you are sending more at any time than advertised window. Yeah.
You cannot send more than this, but your window size can be bigger.
Yeah, window can be bigger, but at once you cannot send more than that. Because you see, the window kind of moves like this. If time goes this direction, it will move like this. You see?
No.
Both the front and the back sort of jump forward. So it's okay.
Yeah, that's base.
Yeah.
It can't see clearly. Here is a faster retransmission packet. Here is a blue dot, but you can't see it. Faster retransmission happens when you receive 3 duplicate ACK. It means you send this packet after the 4th acknowledge at the same sequence number. This is faster retransmission. And then we get through the faster recovery to another top sender. See here, it's different. When you send a packet, your window size is not 2 packets, just as what we see before. You can send 6 packets now. This is because the faster recovery. Fast recovery means when you receive duplicate ACK. After you receive 3 duplicate ACK, you faster retransmit this packet. And after that, when you receive each acknowledgement, you can increase the window size. It cannot prevent you from this plot. Yeah, it can see more clearly here. This is the point you faster retransmit. You decrease the threshold to this value. The threshold is decreased to the flat size. Flat size means the smaller one of the send window and the receive window. This is the flat size. Now flat size is here. So you decrease the threshold, the red line, to half of this window size. This is the same point you faster retransmit. You can see at the same time. Yeah. Here is the faster retransmit packet, and here is what you decrease the window threshold. And after you decrease threshold, when you receive an acknowledge, you can increase the window size by 1. Each duplicate acknowledge increase the window size by 1. And only after this point, you begin to send the packet. Yeah, but it's too complicated to explain why. Because only after that, you have already so many packets in the network. So when the window size is here, you cannot send. Only after your window size is bigger than what you have already sent, you can send more. You can only explain this way. And at this moment, the fast retransmit is resumed because you have received acknowledgement. Let me show you this. At this moment, you have received the acknowledgement for all these packets. So you can begin a new phase. Like you have to decrease the window size again. This means you resume from the faster retransmit. So you start from this threshold and increase the window size 1 packet per window. This is congestion avoidance because you have lost 1 packet. So you have to do a congestion avoidance here. So from the plot, we can see at this moment the window size is 6. And here it's 7 and here it's 8. This is what we say congestion avoidance. And by now,
something. You see, this is a nice point leading to what Young is going to talk later. TCP doesn't know why packet got lost, but it immediately takes an action and slows down. So when you lose a wireless link, you have a problem. You can already see why. And there's more examples of how, there's more ways it could happen actually.
here is an example of timeout. In this plot, we see the packet loss went earlier at this place. So, because the window size is very small, you cannot get 3 duplicate ACK. Is that true? No.
Yeah.
You really get 3 duplicate ACK. So here, this packet is a faster retransmit. But this packet cannot faster retransmit because it receives only 1 acknowledgement. So this packet will endure a timeout. Only after timeout it begins to send the packet. a timeout is very bad because you have to decrease your window to one packet again. Here we see the congestion window plot. The window keeps very low, you see, because you lost the packet very earlier. The window size is only 2 at this moment. So it just think the network is heavy blocked. So you can increase the window very slow after 2 packets. That is called very bad performance. You see the packet, the throughput very low. You can send only a very small amount of packets. So that's almost all the flow control. I think I have covered all this slow batch congestion avoidance. Yeah, I think that's it. Any question?
Okay, I mean, this is all on the web, as you can see, so you can, there is another longish page that explains kind of more mathematically how it works and stuff. All this is run by Hongbo, these examples, and all the plots were made by Hongbo, so she's really a person who can advise if you feel a problem with PCP. Well, thanks a lot.